Welcome to the new lesson in Chapter 11, Thermal Properties of Matter. Today we are discussing specific heat capacity of a substance. Specific heat capacity of a substance is the amount of heat required to raise the temperature of 1 kilogram of substance by 1 degree Celsius or 1 Kelvin. We all know that when an object is heated, its temperature increases. The more it gets heated, the more its temperature rises. So, the amount of heat required to raise the temperature of 1 kilogram of substance. So, that is the point to be noted. To raise the temperature of 1 kilogram of substance by 1 degree Celsius or 1 Kelvin. How much amount of heat is required to raise for that purpose? That heat is known as specific heat capacity. So it has the SI unit joule per kilogram per degree Celsius. Now consider an object of mass m which is heated through a temperature difference of delta T. Let the amount of heat given to the substance be delta Q. So, from the definition of specific heat capacity, we can write that S is equal to delta Q divided by M delta T. So, we can write this equation in another format, that means delta Q equal to Ms delta T. This equation gives the amount of heat required to raise the temperature of m kilogram of substance through delta T Kelvin. Here S stands for specific heat capacity. The quantity specific heat capacity will be a constant for a particular substance. So for different substances, the specific heat capacity will be different. The SI unit of specific heat capacity, it will be joule per kilogram per Kelvin or joule per kilogram per degree Celsius. The quantity heat capacity represented by capital letter S, it is the amount of heat required to raise the temperature of any substance by 1 degree Celsius or 1 Kelvin. So any mass of substance. So here it is not like 1 kilogram of substance. To raise the temperature of any mass of a substance through 1 degree Celsius or 1 Kelvin, that amount of heat is termed as heat capacity. So the expression for heat capacity is S is equal to delta Q by delta T. So SI unit of heat capacity is joule per Kelvin. Now molar specific heat capacity. It is the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius or 1 Kelvin, and its unit is joule per mole Kelvin. So if we write an equation for molar specific heat capacity, it will be C is equal to delta Q divided by N delta T, where C stands for molar specific heat capacity, delta Q stands for amount of heat supplied to N moles of the substance, and delta T is the temperature through which it is raised. Now this molar specific heat capacity, it is of two types, that is at constant volume and at constant pressure. It is actually for gases because gases can be heated in two methods. In first method, it will be heated at constant pressure, and in the second method, it will be heated at constant volume. So likewise, specific heat capacity for gases, molar specific heat capacity for gases will be of two types, that is at constant volume and at constant pressure. So specific heat capacity or molar specific heat capacity at constant volume, it is represented by Cv. It is the amount of heat required to raise the temperature of 1 mole of a gas at constant volume by 1 degree Celsius or 1 Kelvin. So that is how molar specific heat capacity at constant volume is defined. And molar specific heat capacity at constant pressure, Cp, It is defined as the amount of heat required to raise the temperature of 1 mole of a gas at constant pressure through 1 degree Celsius or 1 Kelvin. Both Cp and Cv, they are represented in the unit joule per mole per Kelvin. And both Cp and Cv, it will not be same for a gas. It will be different. The relation between Cp and Cv, that means molar specific heat capacities at constant pressure and constant volume of a particular gas, it is known as Mayer's relation, and that relation is Cp minus Cv equal to R, where capital letter R stands for universal gas constant, which is 8.314. Here we have the table showing specific heat capacities of different substances. So we can see that the substance with highest value of specific heat capacity is water. Water is having specific heat capacity 4186 joule per kilogram per Kelvin. So that is the highest value, and because of this highest value of specific heat capacity, we have got some advantages of this. It is because of high specific heat capacity of water, it is used as a coolant in automobile radiators. So it can absorb more heat, that's what. And in the same way, sea breeze and land breeze, it occurs also due to this high specific heat capacity of water, because when we compare land and sea water, we can see that water gets heated slowly compared to land, because water has got more specific heat capacity. More heat is required to make it heated. So these are the advantages we say. Now, calorimetry. Calorimetry, it is the branch of physics which deals with the measurement of heat. And calorimeter is a device used to measure heat. Now, the principle which we follow in calorimeter, it is this. That is, when a hot body and a cold body, when they come in contact, hot body will be losing heat energy and the cold body will gain heat energy. So the heat lost by the hot body will be equal to heat gained by the cold body, provided no heat is radiated to the surroundings. In that condition, heat lost by the hot body will be equal to heat gained by the cold body. So this is the main principle which we use in calorimetry in measuring heat. And calorimeter, it consists of a metallic vessel and a stirrer. Stirrer is an object which we use to just stir the liquid which we take. Most probably it will be water, and they are of same material. Both the vessel and the stirrer are of same material, say of copper or aluminium. And the vessel will be kept inside a wooden jacket which contains heat insulating materials like glass, wool, etc. This heat insulating material we use in order to make it sure that no heat exchange is taking place between this calorimeter and the surroundings. And we have an opening in the outer jacket through which a mercury thermometer can be inserted to the calorimeter. And when a solid hot body is inserted in the calorimeter, heat lost by the hot body, that substance, will be equal to the heat gained by the water and the calorimeter which we have kept inside the wooden box. Now we have a problem. Example 11.3. A sphere of aluminium of 0.047 kilogram placed for sufficient time in a vessel containing boiling water so that the sphere is at 100 degrees Celsius. It is then immediately transferred to 0.14 kilogram copper calorimeter containing 0.25 kilogram of water at 20 degrees Celsius. The temperature of water rises and attains a steady state at 23 degrees Celsius. Calculate the specific heat capacity of aluminium. So this is the question given. So in this question, it's given that sphere of aluminium is kept in boiling water, so that when we take it from that boiling water, its temperature is 100 degrees Celsius. So aluminium sphere is at 100 degrees Celsius initially. Its mass also is given. And it is transferred to 0.14 kilogram copper calorimeter containing water at 20 degrees Celsius. So initially water is at 20 degrees Celsius. So copper calorimeter also will be at 20 degrees Celsius. Then when aluminium sphere comes into contact with this calorimeter and water, there takes place the heat exchange between this sphere and aluminium sphere and copper calorimeter and water. So heat is lost by the aluminium sphere and the heat is gained by the copper calorimeter and the water. And finally it's given that all the three, they reach at a temperature 23 degrees Celsius. And we are asked to find the specific heat capacity of aluminium. The important equation which we use in solving this problem is this: delta Q equal to ms delta T. Here m is the mass of the substance, S is the specific heat capacity of the material, and delta T is the temperature difference. So to raise the temperature of a substance whose mass is m through delta T, how much heat is given, or when it is cooled through delta T, how much heat is liberated. That's what this equation gives. So we start with the concept that heat lost by the hot body is equal to heat gained by the cold body. So heat is lost by that aluminium sphere, and here the heat is gained by the copper calorimeter and water. So we write the expressions for the three and we write it as an equation. So for the aluminium sphere, it is actually the specific heat capacity of aluminium which we need to find. All other specific heat capacities we can take from that table which is given in the textbook. So we have, for the aluminium sphere, its mass is 0.047 kilogram, and initially it is at 100 degrees Celsius, and finally in the steady state its temperature has become 23 degrees Celsius. So the temperature difference for aluminium sphere, it is 100 minus 23, it is 77 degrees Celsius. And we assume its specific heat capacity to be SAL because that is what we want to find. So the amount of heat lost by the aluminium sphere, that is ml or m1 SAL delta T equal to 0.047 into SAL into 77. We keep it as such because SAL we do not know. Now we consider water because heat lost by the aluminium sphere is gained by water and calorimeter. So we take the case of water. For water, its mass is 0.25 kilogram and its initial temperature, it is 20 degrees Celsius, and final temperature, it becomes 23. Similarly, the case with calorimeter, its mass is 0.14 kilogram and its initial temperature is 20 degrees Celsius, and finally it is coming to a temperature 23 degrees Celsius. So for both the calorimeter and water, the temperature difference is 23 minus 20, that is 3 degrees Celsius. And from the table which we have seen earlier, we get specific heat capacity of water, that is SW, as 4.18 into 10 raised to 3 joule per kilogram per Kelvin, and the specific heat capacity of copper calorimeter as 0.386 into 10 raised to 3 joule per kilogram per Kelvin. So knowing all these things, we can write the expression for heat gained by water and calorimeter. So together they gain this heat from hot aluminium sphere. So we have the heat gained by the water and calorimeter as M2 SW delta T2 plus M3 SCU delta T2. Here SW stands for specific heat capacity of water and SCU stands for specific heat capacity of copper. Now substituting we have. So the thing is this, delta T2 is common, we can take it outside, and substituting we have 0.25 kilogram into 4.1218 into 10 cube plus 0.14 into 0.386 into 10 cube whole into 3 degrees Celsius. So by using the principle of calorimetry, we have 0.047 kilogram into SAL into 77 equal to that heat gained by that water and calorimeter. Now we need to solve this equation and get that SAL. So we get SAL as 0.911 into 10 cube joule per kilogram per Kelvin. That's what is written as 0.911 kilojoule per kilogram per Kelvin.